So we're looking at a quiz next Tuesday that's going to be on this max-min idea, local max-min, number lines, and then also this global max-min, list of candidates thing that we started yesterday. So we're going to work on that a lot today. We're also going to introduce one new thing today, one other new thing that's in chapter 2, and it's called differential equations. It's a little bit of a side trip, but it is involving derivatives, right? It especially involves the exponential functions, and so it definitely fits right in with this, but it's a little bit over here compared to the max-min stuff. Okay, so we're going to start with that a little bit today, and do just a little bit. That's one of those topics that's going to continue to spiral throughout the course. As we learn more stuff, we'll come back and revisit differential equations a little bit. Today, we're just going to get introduced to them and do a little bit with the idea of differential equations, okay? But then, so after next Tuesday's quiz, we're going to just be practicing all the different derivatives. For example, we haven't figured out yet how to handle x squared times sine x. How do we do the derivative of that? Because we've said, if it was x squared plus sine x, we can do that. We can do x squared would be 2x plus cosine x, and we'd be done. If it's plus or minus, we can just do their individual derivatives. When they're multiplied together, we can't do that. We already talked about that. So one of the things we'll learn in chapter 3 is how do we handle something like that? Okay. Another thing we haven't done yet is how do we handle something like that? We talked about if you put a 2x inside the sign, what do you do with that 2? You kick out that 2, right? Because it affects the slope. What we haven't talked about is what happens when there's a function inside of another one of these functions, rather than just a number times the x. What do we do in those cases? So that's stuff we have to learn in chapter 3. Now, it's not going to take very long once we figure it out, but we have to do that. Then we're going to take our quiz in chapter 3. We're going to take one quiz overall in chapter 3, and it's called a gateway test. And a gateway test, the word gateway means you have to go through, you have to get through it. In other words, you have to score a certain score or keep taking it. Okay? So there's going to be 10 questions, and you got to do the derivative, and you have to get 8 right to pass it. Okay? And if you don't get 8 right, we'll take it one time in class, and then after that, you got to do it outside of class. Now, it is possible that you don't have to pass it. You may end up just having to choose to take a lower grade. And that's what sometimes people will do. But I won't go into great detail with it, but it's based on your grade you get then is based on how many attempts it takes you to pass it. Okay? So if you get 8 right, 9 right, or 10 right on the first attempt, it doesn't matter. That counts as passing it. So if you get 8, 9, or 10 right out of 10 on the first attempt, you get 30 out of 30 in the grade book. Okay? And then if you don't get 8 out of 10, you have to take it again. And if you get 8 out of 10 on that attempt, you get an A still in the grade book. You get 27 out of 30. Okay, and I think I actually give you 2 attempts to get that A, right? So you actually have 3 attempts to get an A, right? You got 8 out of 10, the first or better, the first go, you get 30 out of 30. You get 8 out of 10 on either of your next 2 attempts, and you get 27 out of 30, which is a 9. And then 2 more attempts after that to get a B, so that'd be 24 out of 30, and so forth, so on. Now, at some point, if you've taken more than 5 attempts and you still haven't passed it, then I will take just your best grade. So in other words, let's say you got 5 out of 10 was the best you ever did. Well, then you get a 50%, 15 out of 30. Okay? Most people by then, if you've been trying at all, will have passed it by the time you get to that. Okay? If your best is 7, well, that's right. But by the time you've got to 6 or 7 attempts, the best you can get is a 70 anyway, right? So if you've already got a 7 out of 10, you kind of do that. So that's what we'll be working on after the quiz next week. So the next part of next week, the last part of next week, we'll be working on that. Okay? I'll probably take that quiz maybe the early part of the next week. Okay, so anyway, looking ahead, that's kind of what we have coming up. So being able to do these derivatives and follow these rules really, really important here. Okay? All right, so some of the homework here, let's go through. I don't know which, if you have a question. I tell you what, I've picked out a few. Let's talk about these. Okay, here was number 6. So, you know, when on number 6, they asked for h prime of 10. Okay, what is h Use theorem 12. Now I'm never going to use language like that. Theorem 12 is just the rule for the derivative, okay? But h prime of 1/10, h prime of 1. So anytime, you'll hear me say this a lot this year. If you want to find h prime of 1/10, what do you have to find first? If you want to find h prime of 2, if you want to find h prime of 7, if you want to find h prime of 10, what do you have to find first? H prime of x, right? You got to find h prime of x, right? You got to find h prime of x, so you can then plug in a 2 or a 7 or a 10 or a 1/10, right? So the first thing we do is we have to follow the rule. So log base 10 of x means 1 over x times 1 over ln 10 because of the rule that we had yesterday right there, okay? And then you plug in a 1/10 in for x. So 1 over 1/10 would be 10 times 1 over ln 10, or most of you would probably write that as 10 over ln 10. And just leave it like that. That's fine. That's fine. Doesn't matter. Okay? Now, if you get, like, what was another one you had to do? H prime of 1. Okay? Well, that'd be 1 over 1 times 1 over ln 10. I mean, you wouldn't leave it like that, probably. You know, but there could be things to simplify sometimes, but that's good enough. Okay, so that was a point I wanted to make there. Here's number 16. Now, it's kind of funny. We'll never see functions like x to the e. You rarely see this, but they're really trying to make a point here. I really like this problem because it really makes you think about the rules. Okay, so 16 was to find f prime. And so what's the derivative of e to the x? E to the x. What's the derivative of x to the e? E times x to the... See, because those are two totally different things, right? E to the x is an exponential function. It's a number raised to an x. And so therefore the rule is this. This is x raised to a number. This is the power rule. This is x raised to the n. So you bring the number down in front, you drop the power by 1. They're two totally different things, right? And I sometimes see people with the e to the x. Well, we don't usually screw up e to the x. That one we're pretty good at. But what I see people do is they take 2 to the x and they want to bring the x down in front and then make it x minus 1. No, that's not what exponential functions are, right? Exponential function 2 to the x, you use this rule right here, okay? All right, so so it really makes you think about the rule. What kind of function are you looking at? Plus, what's the derivative of e? So what's the derivative? See? And that's another little lazy shortcut we say sometimes, because I'll say that probably. I'll say, what's the derivative of e? And, we'll say, well, it's e to the x. And I should be saying, what's the derivative of e to the x? Is e to the x. But e's just a number. This is e to the first. That's just a number. It's not a function. Well, it's a function. It's a constant function, right? And the derivative of a constant is 0. And so we usually wouldn't even put the 0 on. Okay? I was great, again, looking back on the quizzes, I don't remember the exact problem, but for some reason, a problem like this has given us fits. I had a number of people, this wasn't the exact problem, but on the quiz, if we're doing the derivative of this, what is it? It's 12x squared. Now, that's another thing that sometimes people forget to do, is put that power up there. They get focused on the 3 times 4, and they forget about the power there. And then what? Minus 8. Had a bunch of people just drop this off completely and not put anything there, which was strange, right? So anytime you have just plain old x with a number in front, that is the derivative, that is the slope, whatever that number is. Okay, so it's that. Anyway, just little mistakes like that we want to make sure. Problems are going to get hard enough without making little mistakes on these things. Okay, and then what was the number you had to do the second derivative then? What number would that have been? Right, there's one later that you had to go back and do the second derivative, right, of that same problem. Okay, so that would have been what, 28? No, 22. And then 28, did we do 20? Did we go down all the way to 30? Yeah. Did we do the antiderivatives? Yeah. Okay, yeah, and we do want to talk about the antiderivatives. I didn't put them on this last quiz, but that's one of the things that would go on the next quiz. So we'll have some problems like this where you have to do the derivative just with the rules, and then there's going to be some, there might be a few with antiderivative also. Okay, so let's talk about that. So 22 here would be the derivative of this, so that's still e to the x. And then what do you do with this? Well, what do you do with the number in front? Just hangs out there, right? So the e's just going to hang out there, and then we're going to bring the e minus 1 down, right? Times x to the e minus 2. And then, of course, the 0 is gone. Yeah, there you go. Yeah, you could distribute this e through here, but it's not really necessary. Okay, so there you go. Now, what would be the antiderivative? Okay, so this would be number 28, right? Number 28. So now we're going back up to this one. Well, what's the antiderivative e to the x? Now remember, whenever you're doing antiderivative, it's not really so much a rule as it is think about what you would need to have so that when you do the derivative of it, you get back to this thing in the box. So we're looking for something down here that when we do the derivative of it, it'll give us that thing in the box. That's so we can check. So whenever you do an antiderivative, it's all about figuring it out and then checking. Okay, so what about x to the e? We kind of had a little rule on that. We said for a power one, the reverse would be what? Raise the power, and then what? Divide by that new power. So if you had x to the third, we said, well, that'd be 1/4 x to the fourth. And so what you do is you raise the power up 1, and then you divide by the new power, right? And so that'd be 1/4 x to the fourth. That way, when you do the derivative, the 4 comes down, cancels that, and then you get x to the third. So same thing here. We'll raise that up to e plus 1, and we'll divide by e plus 1. Now, I would probably a lot of times want to write that 1 over e plus 1 times x to the e plus 1. Okay, and then what's the antiderivative of e? Not e to the x, but I think of it this way. Again, e is just a number. What if this was a 7? What's the antiderivative of 7? 7x. We were just talking about that right down there. 8x, the derivative is 8. So the antiderivative of 8 has to be 8x, right? So it's kind of like, think of it this way. If you had a 7, if you want to think of the rule, really it's just common sense. But if you had a 7, there's like an invisible x to the what here? There's an invisible x to the 0, right? And so what would you do? You'd raise that up 1, divide by 1. And so you get 7x, okay? But it's really just kind of common sense. If you have 7, the antiderivative is 7x, because then you do the derivative of 7x, you get 7. So this is going to be e times x, not to be confused with e raised to the x, okay? And then, what did we say about an antiderivative we should always tack on at the end? Let's get in the habit of doing that right now, because there could have been some constant out here that we don't know what it was. Now, the directions, I think, take care of that for you. If you leave off the plus c, okay, you really shouldn't, but look what the directions said. They said find an antiderivative of those problems. So if you left off the c, you'd be finding one of the antiderivatives, but there's an infinite number. Okay, later on we'll call that find the general antiderivative, and then you want to put on the plus c. Yes, sir.
So back to the e, like just e.
Yeah.
So could it also be 1/2 e squared?
For the no, because this is just 2.718 something something something. It's just like having a 7 there. So if you said the antiderivative of 7 would be 1/2 times 7 squared, right? You'd be saying the same. That'd be the same thing, right? Because you're thinking of e as a letter, not a number. You know what I mean?
Well, I just raised it to, it's like e to the power 1.
It is.
And then just did that same rule.
Here's the key, though. With respect to x. So it's that rule only fits if you have x, your variable, raised to something. And e's not a variable. Okay? Because again, do the derivative of this number. This is 49/2. What's the derivative of 49/2? It's 0. It's not 7. Okay? All right. And that's why I love this problem, because it really makes you think about what the rules are. Even though we'll rarely ever see e as just a number somewhere, and we'll never hardly see x raised to the e, it really makes you think about them. Another one we sometimes see is x raised to the pi. Same thing. You bring a pi down in front and drop the power by 1. That kind of thing. Okay? Because pi is just a number. Okay, here's another one, 18. So let's talk about this again. What do we got? We got a number times an exponential. So a number out in front just hangs out there. And then we do the derivative of the exponential. Well, the derivative we're looking at, the rule we're looking at is this one right here. Right? We got 3 raised to an x and some other stuff in there. But we always leave the inside alone. So the x minus 1 just stays alone. So that's this part right here. And then we have to tack on a ln 3. Okay, which again, ln 3 is just a number. ln 3 is just a number. Okay, just like 2 is just a number here, right? And then this minus 1 in there, that doesn't mean anything. We have to do anything with that. Only if we're multiplying the x in here would we kick something out. So we don't have to kick anything out, right? So there's f prime. Okay, what's the next one? F double prime. That should be number 24. Well, we got a number and a number sitting in front. Now, the ln 3 isn't in front, but we can move it in front. So those just hang out there. So the 2 and the ln 3 just hang out there. Okay, and now I do the derivative of this. Well, I'm back to this rule right here. So what do I need? I need the 3 to the x minus 1. That's that part of the rule. And then I got to tack on another ln 3. Okay? And there you go. And you can just leave it just like that. Okay? All right, what is the antiderivative? Well, this is where the guess and check kind of comes in. We're not raising the power up. We're not doing any of that, right? That's the power rule. That's x raised to a number. So we just have to be doing stuff that we think. We just guess. We say, well, geez, exponential is really its own derivative. We have this other little thing we tack on, but we'll deal with that in a minute. So I'm guessing, this is my guess. I think the 2 is just going to hang out there, and then it's its own derivative. So I think it's going to be this. Now, I'm pretty sure I'm wrong because I don't think it's going to be exactly the same thing. But I'm just going to guess this, and then I'm going to check it. So I'm going to check it. So what I'm going to do is I'm going to do the derivative of this right now. Okay, let's do the derivative of this. Well, what would I get? I'd have the 2 here. Then this would be its own thing. And then I'd have to tack on a ln 3. And I'd be like, oh, well, that can't be right then. If I do the derivative of that, I get that. Well, what's it missing? It's missing the ln 3. So I know when I do the derivative of this, I'm going to end up with an ln 3 tacked on, but I want it to go away. So what must have been sitting here? What must have been hanging out here on this one? There must have been a 1 over ln 3 hanging out here. Now, don't confuse that with this rule. That's a whole different rule down here. There must have been a 1 over ln 3, because remember, 1 over ln 3 is just a number. 1 over ln 3 is just a number. Okay, so when it's sitting here on this function along with that 2, those are just numbers. So if I go to do the derivative of this red thing now, if I go to do the derivative of this red thing, the 2 and the 1 over ln 3 are just going to hang out, right? Because they're just numbers. So the 2 and the 1 over ln 3 are just going to hang out. And then I'm going to do the derivative of that, which would be 3 to the x minus 1. And according to the rule, I have to tack on an ln 3. Oh, there we go. When I tack on the ln 3, it'll cancel that, and then I'll get what I want. I'll have my 2 and that. Okay, so it's, again, antiderivative is kind of like reverse. And so the derivative of an exponential, you tack on an ln 3, it kind of makes sense when you do the antiderivative. You might have to tack on a 1 over ln 3, the reciprocal, right, to kind of cancel that. All right, so that is how you do that, but it's really just thinking it through. It's kind of a guess and check. Okay, what about? I don't think you had one of those, but I mean, let's just do a little simpler one. Let's say we had sine 2x was our little f, and we wanted to find big F. Well, what's a first guess of what it probably is, just to get you started? Probably a cosine, right? Pretty sure it's going to be a cosine, right? And we know the inside never changes, right? So we know we're going to have that, right? So that's a good start right there. So let's just use that as our guess. Okay, and now let's check it by doing the derivative. So what's a derivative of cosine? Oh, oops, so I better get a negative in there, right? Better get a negative in there. Okay, see, so my check is telling me what to do. So, okay, derivative of cosine is negative sine, but that'll be sine of 2x. But when I do the derivative, I'm going to have to kick out a 2. Oh, there's no 2 there. So what must there be here? There must be a 1/2 sitting here, and then I need my negative. There must be a 1/2 sitting here, so that when I kick out that 2, that 1/2 will cancel it. See the thought process there? Okay, so now I feel pretty good about that. Then I could put a plus C in there, whatever. But now I feel pretty good about that. And then now I check it and I say, oh yeah, negative cosine derivative be sine, kick out a 2, it'll cancel the 1/2, and I'll be back to where I wanted to be. Okay, so that's the thought process when you do an antiderivative. We're going to do antiderivatives in great detail later in the year. So this isn't, this is just kind of a beginning, and we'll do a few on the quiz, but not a huge deal. Okay, number 20. So now we got this rule right here. So we got log of a base. A 3 is just going to hang out. So my rule says do 1 over x, or 1 over the inside, that is, and then 1 over ln2. Okay, so that's f prime. Okay, so pretty basic. And then what do we got? Again, we got numbers that are just going to hang out. So this, now I can put that together. 3 over ln2 might be better to do that. They're just going to hang out. And now I got to do the derivative of that guy. Well, how do I do the derivative of 1 over x? I got to write it that way, don't I? And then, so now what? Well, I bring the -1 down in front. Make sure I put parentheses around this. X to the -2. Now I think you ought to probably bring that negative around in front and put it on that 3. Maybe put -3 over ln2. Be a good habit to get into. X to the -2, I'm fine with you leaving that. If you want to drop it down to the bottom, that's fine. Okay? And then, was it number 32, you had to do the antiderivative? Or did we do it? We didn't do an antiderivative this one. Yeah. No, we can't. Because really there is no antiderivative. No easy or fundamental antiderivative of the log. So we can't. Because think about what we have to do. We'd have to get some function that when we did the derivative gave us a log. Look at our rules so far. Do we have anything when we do the derivative we get a log? Nothing, right? Even the log ones, when we do the derivative, we don't get a log. Other than this number, but that doesn't count. Okay, so that's why we can't do the antiderivative. Okay, let's look at number 35. I want to go through that one. And then, so kind of a little bit of a story problem here. So January 1, 1960, the population's 50,000. So we've got this function represents the population of this place since 1960. So what was the population on January 1st, 2000? Well, wouldn't that be doing this? P of 40, wouldn't that be saying plug in a 40? Because 1960 is times 0, so 40 years later, so time is 40. Okay, now I want you to get used to this notation here, using your function notation, so this would be really important to show your work. Okay, so I think we ought to say P of 40. Okay, well that's easy, so get your calculator out. This is a calculator one. Okay, you should always try to not use your calculator as much as you can until it comes time you're like, okay, I need to use my calculator. Okay? All right, so just type in 50,000 times 0.98 raised to the 40. What do you get? Everybody got it? $85. That's to the nearest person. Rounded to the nearest, which makes sense, right? Okay. So obviously it has decreased. So much for the name Boomtown, right? 22,285. And why did it decrease? 0.98, right? Number less than 1 in an exponential. If this base is less than 1, it's going to be that exponential decay kind of situation, right? 0.98. All right. So now it says, at what rate was the population changing at 2000? Well, what we want to get in the habit now of doing, being able to do, is identify that as a derivative question. So at what rate was it changing is P prime of 40? And I'll ask the question again. Before you can find P prime of 40, you need what? P prime of T in this case, right? So now our rule would be there'd be a T on the bottom here with respect to T. That just means T's are variable, right? Our input variable. So we need P prime of T. So P prime of T, well, what do we got? We got a number just hanging out in front. So that's just going to hang out there. Times, and then which of these rules we have up here? 1, 2, 3, or 4? It's number 2, isn't it? So this is 0.98 raised to the t. So that's just going to be 0.98 raised to the t times ln of 0.98. Okay, so type that into your calc. Now we're going to stick a 40 into there. So now we're going to put a 40 in for t, and we're going to type that in. 50,000 times 0.98 raised to the 40 times ln of 0.98. So this would be a type of question I could ask on the quiz. Just pretty simple. Give you the equation, ask you a little bit about it, where you just have to plug some things in and use your calculator, but you got to be able to do this derivative. Now, in this case, you get to use your calculator, so let's don't forget, I think somebody, and I don't remember if it was in here or the other class, if you're using your calculator, if it's a calculator part of the quiz, then it's perfectly acceptable to come right over here. Now, usually this takes long. If you know your derivative rules, this takes longer. But if you're not real confident, you might want to let your calculator do it. Now, right now, I think the emphasis should be on you should be trying to do these without your calculator. Okay, so I'm going to do this with respect to t. So here is what we have. Now notice they do it a little differently. They took the 50,000 times the ln 0.98 already. Okay, and we got that. And then remember what I showed you yesterday, if I want to plug a 40 into this, now it would be real easy to just do this and now delete that t and put a 40 there. That would probably be the smart thing to do. Just delete the t, put a 40. But I'm going to do that vertical bar thing. Okay, vertical bar with t equals 40. It's going to be the same thing. It's going to put a 40 in. Okay, and there we go. Negative 450. And what does that mean? Now, first of all, it says the population increasing or decreasing. Look at the chart. When p prime is negative, p is decreasing. The population is decreasing because it's negative. What would be the units on that 450? People per year. So in 2000, in the 40th year, they are losing people at a rate of 450 people per year. Okay? Simple. I mean, just using our derivative rules, plugging in, answering some questions.
So if we ever did use our calculator, how would we show our work for that?
Okay, good question. So if you had done, if you had used your calculator to get this derivative, then you would probably just write this down on your paper as p prime. And then you would, and again, showing your work is writing this notation here. Put p prime of 40. That shows me you're communicating what you're doing. You're telling me you're putting a 40 in, right? And then I can tell what's going on. It's like that quiz, first quiz we had, or one of the early quizzes where we had the phone call. And some of you got some partial credit because I could tell you were plugging in 40.5 into the function because you wrote it out. Other people, you just got an answer, and I had no idea where it came from and what you were doing, and you missed it, and I did, and you lost more points probably. So you show what it is that you're doing on that. Okay. What was it? Was this 10 through 13 on the next page? This was on 2.7. Yeah, this was this problem right here. Okay. So let's walk through that a little bit. As I was going around, I saw some good, some bad, things here. But as you go through the problems, are there stationary points? Are there inflection points? Are there local max? Are there local min? That's what 10 through. So as soon as I read a problem like that, and I see those different things right away, the chart comes to mind. Local max, local min, inflection points. So right away I think number lines, right? I think number lines. So I'm going to do my derivative. So the derivative of x, 1 plus cosine, set it equal to 0. I'm going to solve it. Where does cosine equal -1? Well, that'd be a pi. Now, notice that this is where the trig stuff becomes important because they said we're looking from -5 to 5. Okay? Well, all the way around is 6.28, right? 2 pi. But also we got to go negative too, which would be the other way around. Or if you just want to look at the cosine graph, here's the cosine graph. Right? Where does cosine equal -1? Well, back here and right there. So at pi and at -pi. Okay? So we have to be able to look at our interval, and we have to be able to think in the unit circle that way. So over here is where cosine is -1. Well, that's pi, but that's also -pi, this one. Okay? So we got to keep that in mind. right? And then, so that's our number line, so we go ahead and put negative pi and pi on a number line. Now, I picked some numbers in between here, and I'm gonna plug those right into here, right? So negative 2 pi, well, cosine negative 2 pi and 2 pi and 0, they're all 0, 2 pi, negative, they're all over here. Cosine is 1 in all of those, okay? So what you have is 1 plus 1. And here's another thing to think of. So see how you get plus, 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 right? But think of it this way. Here, now, hey, I love the number line. And if you use a number line, that's great. But the number line is not the only thing we can do. It's just a pretty good, useful thing. So I like using it. Think of the graph of 1 plus cosine. What's it look like? It's shifted up 1. So isn't it always going to be positive? It'll be 0 a few times, but it'll always be positive. So right there, so without even a number line, we could have said 1 plus cosine is shifted up. It's always going to be greater than or equal to 0. So f has to always be increasing. So right away we could say there's no local maximum in, right? Just from that, without even doing the number line. Okay, fine. That's okay if you didn't think of that or didn't see it. That would be okay. But the number line's great too. All right. And so since there's no changes in sign, there's no local maximum. Now, did it say 10 said did it have stationary points? Yes. So there's your answer to 10. So 12 and 13 would be no. There's no local maximum. Okay, because it doesn't change sign. Okay, and then number 11 was inflection points. Okay, so we need the second derivative. So we do the derivative of this. That'd be negative sign equals 0. I would divide by negative and get sine equals 0. Where does sine? So that's pretty easy. Sine equals 0 is the y, so that would be, that'd be here and here as well. So that's interesting. It's the same points, isn't it? Same places, but 0 also. Okay, so where does sine equal 0? That'd be at 0, at pi, also at negative pi. 2 pi is outside of our range. 6.28 is outside of our negative 95. Okay, so I put those on a number line. Now, here's something you want to be careful of. Where do I plug these values in? We don't want to plug them into here, right? Because what did I do here? I divided by negative. This is our second derivative right here. Now, does that make a difference? Well, not for inflection point it doesn't, but for concave up, concave down it does. So if I put in negative 3 pi halves, negative 3 pi halves, let's see, negative 3 pi halves will be up here. Sine is 1. But then when I put it into here, I get negative 1, right? If I put it into here, I get positive 1. And so my concave up, concave down will be different. Now, for inflection point, it doesn't matter. All we got to do is get a switch and concave. Okay, but this graph's going to be concave down. So make sure you plug it back into that, before you started messing with it or getting rid of stuff. Okay, so they're all inflection points because F double prime changes sign, so F changes. Okay, so again, that's a classic global, like the thing we showed yesterday. That's a classic global max, global min. Let me pull that up. Yesterday we had this right here, right? That's just a great problem for this, right? We got to be able to do this, and it had some trig in it. We got to be able to do it with some trig. We don't really do chart problems with e to the x. With these functions, we don't use those very much because they're not very interesting. Think of e to the x. It just goes like this. There's no local max, there's no local min, there's no inflection points. It's pretty boring when it comes to the chart. But trig functions are, so chances are you're going to see some trig functions. We also could do global max min. That's coming up. All right. So, was this one we had to do? Why do I have this on here? Oh, you know what? I think I did that because we already talked about that. That was because I wanted to do the anti-derivative thing, right? With that, make sure we're going to have a 1/2 out front, right? So what's this? It's going to be 1/2 sine 2x like that, right? Because when you check it, we do the derivative, cosine 2x, kick out a 2, but that 2 will cancel that 1/2, right? So we'll be good to go. All right. All right. So you don't need to write any of this down, but there's 4 main things that we will have on our next quiz. Okay, 4 main things that we'll have in our next quiz. We're about to embark on differential equations right now. Okay, global max min, which we talked about, list of candidates, stuff like that. We're going to do a problem like that in a minute here. Matter of fact, we're going to do it right now. Okay, then the chart stuff, like we just got done doing. Okay, and then just your rules for derivatives and antiderivatives. So you think about that. We just got to do 2 of those 4 things. Okay, we spent a lot of time on our derivative, antiderivative rules. Okay, we just got done doing the chart stuff. Okay, with local max min, number lines, all that stuff. Okay, so global max min's the one we learned yesterday, so let's go through that. So this is a problem, if you want to turn in your book, if you're not there already, page 147. So let's go ahead and let's do this problem right here. This is very similar to the one we did yesterday, but we need to see it again, I think. Okay, and then we're gonna talk about differential equations. Okay, and so at that point, in a sense, after today, we'll have pretty much talked about everything we need, at least introduced it, that'll be on the quiz, right? Now we're gonna need to finish that up tomorrow and then need to Monday too, so, right? So there's not a whole lot more new going. All right, so go ahead and get started on this one. The problem here is, this is like number 37, it's a little different. I think you're gonna do, I think in your homework, I think you've got number 37 to do. So this is very, very similar to number 37. Okay. Okay, perfect. All right, this is very similar to number 37, so that's going to be one of your homework ones. All right, so where do we start? Find global max min. Now, actually, 37 says a whole bunch of stuff. It says draw a graph. Don't worry about that. It says label local. We're not going to label those. It says use exact values. That means this is a no calculator problem. Okay, but it's just saying find the local global points of inflection. So that would be doing all of the chart stuff and everything. Okay, right now I just want to focus on this part of it. For your homework, you'll do all that. Do the local max min, do the number lines, and do the global max min too. But for right now, let's just do this part of it. So how do we start? Find the candidates, which are when f prime is 0 and the endpoints. So our candidates, the places that the global max and min can occur, are at those 2 places. Well, we already know the endpoints. They told us 0 and 2 pi. So all we have to do is find where the derivative is 0. So what's my derivative? 1/2 minus cosine x equals 0. So subtract 1/2, divide by negative, I get cosine x equals 1/2, right? Where does cosine equal 1/2? Isn't it pi thirds, right? It's pi thirds. Sine is 1/2 at pi 6. Cosine is 1/2 at pi thirds, right? This would be the point 1/2 and root 3 over 2. Remember, root 3 over 2 is bigger. Root 3 over 2 is like 0.866. 1/2 is 0.5. Cosine is the x, so you only go over a little bit and up more rather than over and then up a little bit. So it's pi thirds. And then where else? Down here as well. Cosine is positive in these 2 quadrants. Okay, so we're at pi thirds and 5 pi thirds. Again, I offer my assistance if you want to come in and review any tricks. Okay, we're going to have to know stuff like that. Probably going to be one of those on the quiz. Now, it might be on the calculator part. If it's on the calculator part, we can just let the calculator solve it. But you're going to have to be able to do these, okay, at some point in time. Good chance it'll be on this quiz. All right, so those are my stationary points. Okay, so now I can just go to my list of candidates. Now, if I was doing local max min, I would put these on a number line. And then if I was doing inflection points, I'd do the second derivative equals 0, and then do a number line for that. That would give me my inflection point stuff. But for right now, I'm just doing list of candidates. So remember, we plugged these back in the original. So we're going to do f of 0. We're going to do f of 2 pi. We're going to do f of pi thirds. And we're going to do f of 5 pi thirds. back to the original method. So the original, put in a 0, that'd be 0, sine of 0, that's 0. Okay, 2 pi, what's sine of 2 pi? Sine of 2 pi is 0. 1/2 times 2 pi, or about 3.14. Right, because we got to compare these, right? We got to compare what's biggest and what's not, okay? Pi thirds, what's 1/2 times pi thirds? Just multiply across, right? Pi 6. So this would be pi 6 minus, what's sine of pi thirds? Isn't that root 3 over 2? Okay, now, this is no calculator. Okay, well, I think these are some values we should know. Now, number 1, pi is about 3. So what's pi divided by 6? 3 divided by 6 is about 0.5, right? Pretty close. So that's about 0.5 minus, and this is root 3 over 2 is 0.866. So it's 0.5 minus 0.866 is what? About negative, did I do that right? Roughly? Right? We should know that root 3 is about 0.866. Root 2, what's root 2? 1.4, what's root 2 over 2? 0.707, right? 0.707. If you remember when we did those slopes of the sine graph, those are the numbers we kept getting. We kept getting 0.5 and 0 and 1 and 0.866 and 0.707. Root 2 over 2 is 0.707. Root 3 over 2 is 0.866. Okay, just know those roughly. Okay, so we can kind of compare. Usually they're not going to be that close. It's going to be fairly obvious. Okay, what's 5 pi thirds? Okay, so what's 1/2 times 5 pi thirds? 5 pi 6. Now remember, pi 6 we said was about 1/2. So 5 times 1/2, about 2.5. Or you could say pi is about 3, so this is about 15 over 6. Right, which is about 5 over 2, which is about 2.5. So it's roughly 2.5 minus, what's sine of 5 pi thirds? Negative root 3 over 2. So negative 0.866. So minus a negative. So that's about 3.366. Right? So it actually came in fairly close here to what pi was. So it looks like my max is here, and my min is right there. Okay? So, which was at my 2 station. Right? You could graph this and take a look at it and whatever. Even if this was a calculator problem. If this was a calculator problem, let's talk about that a minute. The black, if this was a calculator problem, you would have this down for sure. But then you would probably just go to your calculator to solve it. And then your calculator would give you this. And then you would still do all of this. Now the difference is we would be a lot more confident what those values are because we get exact values. But you'd still have to show all of this, this, and this. You just wouldn't do this in-between step to solve it, and you wouldn't have to mess with this stuff over here. If this is a calculator problem, you'd still have to write out your f prime, go to your calculator and solve it, write down your stationary points, do your list of candidates. You'd still need all that, okay, for your min and max. But you could graph the original and verify, oh yeah, that is the high point in the loop. Okay? All right, so that's a little bit of review of that. So think about the things that are on this next quiz. Global min and max, okay? Chart stuff, and those derivative rules, a little bit of anti-derivative. We've just done all 3 of those things a little bit here already. Okay? All right, so now let's talk about this idea of differential equations. Okay? So, go to your notes, and let's visit that. Now, if there's anything on the homework that I didn't touch on that you had questions about, remind me, maybe even tomorrow if I say, hey, what questions do you have? If you've still got some lingering questions on some of this, we could probably look at that tomorrow. All right. So, differential equation. What is a differential equation? Okay, so first of all, a lot of times we abbreviate it DE. Okay, a differential equation is an equation that contains derivatives. The word differential kind of is related to derivatives, okay? When we calculate slope, which is where derivative comes from, that's called the difference quotient, right? Because we subtract the y's, subtract the x's. There's a word you haven't heard me use much yet, but the act of taking a derivative of a function is called differentiate. So oftentimes we'll say, well, differentiate f means take the derivative, okay? So doing the derivative is often called differentiation, okay? Doing the derivative. So a differential equation is an equation that contains derivatives. So differential means derivative, equation means equation, right? So what does something need to be an equation? An equal sign. So it's got to have an equal sign and it's got to have a derivative in it. If it has those two things, it's a differential equation. We've already seen some. Right here is, don't write this down in your notes. This right here, we just had this problem a minute ago, right? That's a differential equation. It's got an equal sign, it's got a derivative, f prime, right? It's got a prime and an equal sign, it's a differential equation. We can sit here and write them all day long. Now, to be honest, when we do differential equations, we don't use function notation usually, we usually use y's. We use a different output variable. So we had the Boomtown problem, p prime equals 50,000 times 0.98 t to the t times ln 0.98. That's a differential equation. Okay? Now, big deal. So that doesn't seem interesting at all. Well, here's where it gets interesting, and here's where engineers and people like that really work with differential equations, than anything that has to do with rates and those kind of things. So here would be a differential equation right here. P prime equals K times P. Now, what's interesting about that? Well, that doesn't have the input variable in it, like the x or the t. It's got the output variable, like the y. Now, another variation of this one would be y prime. This is actually a famous differential equation we're going to talk about in a minute. So what you have is an equation that has the output variable y in it and the derivative y prime in the same equation. We haven't seen that before. We've had different equations. We've had a y equals equation and a y prime equation. And they always had x's in them, or t's, right? The input variable. But differential equations don't have to have that. Remember, to be a differential equation, it just has to have an equal sign and it has to have a derivative. Well, all of these have that. Okay? All right. So there's a whole, so I could write them all day long. You talk about a quadratic equation. What's a quadratic equation you have to have in it? X squared. If it's got x squared as the highest power, it's a quadratic equation, right? So all kinds of equations have definitions of what makes them. A linear equation has to have highest power x to the first. That's a linear equation. A differential equation is an equation that has an equal sign. It's got a derivative. So I could sit here and I could write these all day long.
That means that like every single equation be a differential equation because every equation has an f.
That's a differential equation. Now, yes, so you could say, if you said y equals 2x, and you could say, technically, isn't that a differential equation? Because y could be the derivative of big Y, right? And technically, actually, we would probably say, no, to make it a differential equation, we wouldn't write y equals 2x. We'd want to write big Y prime equals x, right? So here's what I know what you're saying. You're saying, if you had f of x equals x squared, you say, that's not a differential equation. It doesn't have a derivative in it. Okay, well, instead of writing it big F, or little f of x equals x squared, how about if we wrote it big F prime? Is that the same thing? Those are the same thing. And then you'd say, yes, now it's a differential equation. Okay, yes, that is kind of technically correct. All right, so that's what a differential equation is. So what do you do? What did you spend all of algebra class and trig class doing? If you had a trig equation, or in algebra class you have a quadratic equation, what did your teacher want you to do with it? No, Not always, well, for quadratics, but not always for other ones. If your Algebra 1 teacher gave you a linear equation, your Algebra 2 teacher gave you a quadratic equation, your trig teacher gave you a trig equation, what would they ask you to do with it? Starts with an S. Solve it, right? That's what we do with equations. We solve them, right? We solve them. So, what is a solution? So the question here is, what does a solution to a differential equation look like? Right? Well, a solution, this is where it gets kind of weird. Because this is way different than any equation you've been used to at this point. A solution to a differential equation is the original function I'm not going to write that down, but in terms of the input variable only. In other words, the solution is not a number. That's what we're used to seeing, right? We're used to seeing in a linear equation, in an algebra equation, 3x plus 7 equals 16. We had ways of solving that, right? And we learned, that's what you spend most of algebra and trig class doing, is learning techniques to solve an equation. And typically we get numeric solutions. Not so with the differential equation. The solution to the differential equation is the original function. So, for example, if f prime of x equals 2x is your differential equation, that's our differential equation. Our solution would be f of x. I'm going to erase it. I'm not going to use f prime because in differential equations we hardly ever use function notation. Let's use y. So if our differential equation is y prime equals 2x, then what is my solution? Y equals x squared plus c. So this is what you got to wrap your head around. The solution to a differential equation is another equation, another function. It's the original function without a derivative in it. And it's got to be in terms of the input variable. So if you get one that's got y's in it, so if you get one like this, one down here, you cannot do the antiderivative of this. We can't just say, oh, raise the power up to a 2 and divide. You can't do that because remember, when you do derivatives and antiderivatives, this is where this with respect to becomes important. When you do a derivative or an antiderivative, you do it with respect to x. You do it with respect to the input variable. So when you do a power rule, when you do these things, they have to be with the input variable in there, which is usually going to be x or t. Okay? So when we say, oh, hey, we want the original equation of this, we want y equals what? We can't just do a power rule because this is the output variable, not the input variable. And you can always tell because the output variable is the thing that has the prime on it. Okay? That's the thing that has the prime on it. We never see an x prime, right? Not yet anyway. Okay? But we never see an x prime, right? So the thing that has the prime on it, that's your output variable. So sometimes you don't even know what the input variable is. And in those cases, it doesn't really matter. It could be x, it could be t, whatever. Okay? Sometimes they give it to you this way. Instead of giving it to you this way, they give it to you this way. Just because that tells you then that the input variable is t. So now we know the input variable is supposed to be t. If we just had this, we could probably use any input variable. We could use that for t. Okay? All right. So then the question is going to become, how do you solve those? Well, most of them we're not going to learn how to solve. That's for a differential equations course in calculus. We're not going to learn how to solve. Okay, the only ones we know how to solve right now would be ones like this right here, right? Just simple ones here. We got a y prime, then over here you got x's, right? Like we were just doing in our problems today. Now you can just do the antiderivative. Okay, so let's categorize these differential equations. Okay, so types of differential equations. Okay, these are just my types. These are my classifications. Okay, one is probably should use the word simple. So, you know, you first learn about them, they don't feel that simple. Okay, but in the world of differential equations, they'd be considered simple. Simple DEs that we can solve by anti-derivative. Okay, so that would be like the one I just talked about. Y prime equals 2x would lead you to y equals x squared plus c. Or y prime equals, what was the one we just did a minute ago? Cosine 2x, right? That would lead us to y equals, what was it? 1/2 sine 2x plus c, right? Just by doing a basic antiderivative. But the only time we can do that is if we have y prime equals and then x's on the other side. No y's, no output variables, just input variables. Then we can just do basic antiderivatives. Okay? So those are so we can solve those. And again, remember, to solve it is not to get a number answer. To solve it is to get the original function. Okay? Then there's going to be DEs we memorize. The solution. Now there's only going to be 2 of those. And we're only going to do one right now. So the one we're going to do right now is this one. Y prime equals k times y. Now that's different now than the type 1 because it's got that y. Okay, so this is different. We can't just do an antiderivative. Okay? The solution of this is, turns out, our old friend, the basic exponential. It's a basic exponential equation. It's probably the most famous differential equation that there is. Okay? Now, let's think about it. Let's pretend y was money you put in the bank. Let's pretend y was dollars you're putting in the bank for a number of years. What would be the units on y prime? Dollars per year, right? So y prime would be dollars per year. So this would be the rate that your money grows is proportional to, you've probably done this in science, right? If you've got a direct relationship, a direct proportion, so K is called the constant of proportionality. K is just a number. The rate your money grows is proportional to the amount of money you have. Y is the amount of money you have. Isn't that true? Doesn't your money grow faster the more of it you have? That's what exponential growth is. The more of it you have, the faster it grows. Okay, so it's not the interest rate. K is not the interest rate necessarily, but it's the rate that your money grows. Okay, or I'm sorry, it's not the amount of interest, but it's the rate that your money's growing. Okay, so the more you have, the faster it's growing. In other words, you gain more dollars per year. Same interest rate. You know, somebody getting 6% interest that has $1 million is the same interest rate that somebody has, but the rate the millionaire's money is growing is faster. He's getting more dollars per year, right, than if you had $100 in it. Okay, well, that's a pretty basic idea right there. This is the power of differential equations, why it's used in engineering and to model things, because we can talk about rates in relationship to the amount, right? We talked about derivative as a rate of an amount. You can easily model situations with differential equations. The downside to differential equations, you can't use them to find values very easily. You need the original function to do that. So you can write differential equations to model situations, but you need the original function to be able to work with it. So that's why it's important to solve differential equations, to be able to find the original function. Okay? All right. So we're just going to memorize those. And then the third type are DEs. We don't know how to solve, but can verify a solution. So that's going to be the big thing we want to talk about lastly here, is what if we don't know how to solve something, but they propose or they give us a solution and say, verify that this is the solution. Okay? So this would be all these other ones. This would be something like y prime minus 2y equals x squared, plus y double prime, something like that. I mean, we'd have no idea how to find the original y on something like that. Okay, no clue. But if they told us a y that was the solution, we could verify. And let's go through that example right now. Okay, so let's take, well, first of all, let's go back and compare this to your earlier math career. Okay, because this is what you probably did back in 6th or 7th grade. Okay, 5th grade, I don't know. You wouldn't have had any idea. Now, you knew about multiplication, and you knew about addition and subtraction and all that. Okay? But back then, you wouldn't have had any idea what the solution to that was. Right? Now you do. What's the solution to that? 14. Right? The answer to that is 14. But back before you knew how to solve these, you didn't know how to solve that. But your teacher could say, you probably remember these problems. Is x equals 14 a solution? Is x equals 14 a solution? What would you do to show that it was? Plug it in. I call this a T-chart. Now you're going to hear me call this a T-chart because that kind of makes a T right there. But what you do is you're trying to show that this side is equal to this side. You're trying to show that those two sides are equal. So you're going to plug it in. So when we do these verified problems, you're going to be saying, well, do a T-chart. You don't have to do a T-chart. I just think it's a nice, neat, easy way to show your work. So we do a T-chart. So we go 3 times 14 plus 6 is 42 plus 6 is 48. Over here we get 4 times 14 minus 8. This is 56 minus 8, which is 48. Check. It is a solution. That's what we're going to do. And if the two sides weren't the same, we'd say, no, it's not a solution. That's what we're going to do. Except we're going to do it with a differential equation. Okay? So let's do one. I thought I had one ready to go here, but I'm not sure I do. So let's back up here and grab one. So last bit of information for you. Let's I'll just make one up. So here's our differential equation. Y prime minus x equals 2y double prime. Just leave it at that. Okay? There's a differential equation. We have no clue how to solve it. Is y equals x to the third plus 7x a solution? Thank you. Okay, make a T on that differential equation and see if you can think what to do. All right, so remember back here, we took this is what's hard to remember because it was easy back in these problems because your solution was a number. And when you guys said plug it in, you just plug in the number for the x, right? Well, we're doing the same thing here. So you always got to think back to this. What do? We take our solution and we plug it into the equation. Now, it's hard to do that here because they're both equations. So people get confused on where do I put the t. Always remember back to this example. You take your solution and you put it into your differential equation. You take your solution and you put it into your differential equation. So I put the t right here. What am I going to put here for y prime? I'm going to come over here and I'm going to figure out y prime. It's 3x squared plus 7. So over here, I'm going to plug in a 3x squared plus 7. What am I going to plug in for the x? Nothing. I'm going to put minus x, right? Just like over here, what did I put in for the 6? Nothing. I just brought down the 6. I only plugged in for the x, and everything else I just brought down. So I'm plugging in for the y prime. The x I just bring down. Okay? On this side, I have a 2, and then what am I going to put for y double prime? Y double prime is 6x. So this is a little different than the algebra one also. Is we know what y is. Well, if we know what y is, or what we think y is, then y prime would have to be that, and y double prime would have to be that, right? So off to the side, we're kind of doing that work over there. Okay, and so for y double prime, I'm going to plug in 6x. Well, that's 12x. Does this equal 12x? Not a solution. Because the two sides were not equal. If the two sides came out to be equal, then yes, it is a solution. Does that make sense? That's all we're doing. So we're not going to solve differential equation or anything like that. All we're going to do right now is we're going to verify that something is a solution. Okay? And we do it this way. All right. So homework is on your thing here. So we did those 2 lines that were all together. Now we got 3 lines that are together. 2, 5, 2, 6, 2, 7. So keep in mind what the sections are about. 2, 5 is this new one. That's the differential equations. 2, 6 was the e to the x stuff. So you're going to have maybe a couple problems like the bank interest. We did the one with the Boomtown, I mean. We had the problem with the Boomtown and the exponential equation. So just a couple problems there. And then section 7 is the trig stuff. So section 7 is where we're going to really get the practice on our local max min stuff. So the 2.7 is your trig. And those, to be honest, take the longest probably, those 2 problems in section 2.7, because those are the ones where we're going to do global max min and local max min, inflection point, do number lines, whole thing. So when I come around and look tomorrow, I'm really going to be looking at that, especially, that we were able to spend some time on that. Okay? So, you know, come cheer on the girls' basketball team, and then, you know, go. That's why we made the game early tonight at 5:15, so you could go home after that and get your homework. Unless you're in, where Jane, where did you say that? Like you? I guess you just have to do yours up the or something. That'd be fun. All right. Now, I will make a comment on one of your homework problems, because this always throws people off right off the bat. On your very first problem, number 6, on 2.5, this is on page 129, okay? 2.5, number 6, that differential equation, they write it like this. They go y prime of x, and they go 1 / 2y like that, okay? Well, what that is 1 over 2y. It is not 1/2 y. Okay, it looks like 1/2 y, but it's not. It's 1 over 2y. So if you see that in any of your problems, make sure you understand it's that. Okay, so that very first problem. Okay, and what they do is they give you a couple, they say, here's our differential equation, and then A and B says, show that this is a solution. So right off the bat, right, you're doing a T-chart on that thing. You're going to, for part A and part B, you'll do a T-chart and try to show that those are equal. Okay?